So if we take the limit as n approaches infinity of the absolute value of the general term of a sequence, and that limit equals 0, then that implies that the limit as n approaches infinity of the regular general term is also equal to 0. So, for example, this sequence oscillates between positive and negative values because of this negative 1 to the n power. But if we take the absolute value of this general term, which is just 1 over 2 to the n, the limit as n approaches infinity is obviously 0. So by this theorem, we can say that the limit of this as n approaches infinity is also 0. So the original sequence converges to 0 as well. Because even though the values oscillate between positive and negative, they are still approaching 0 from both sides. So a sequence can be either increasing or decreasing. Increasing means each term is greater than or equal to the previous term, and decreasing means each term is less than or equal to the previous term. And if a sequence is either increasing or decreasing, we say that it's monotone. So the two main ways to test if a sequence is monotone or not is by looking at the difference or ratio of two consecutive terms. Because if the difference between two consecutive terms is positive, that means to get the next term in a sequence, we always have to add a positive number. So it's going to be increasing. And likewise, if the ratio between two consecutive terms is greater than 1, that means each term is greater than the previous term, so again it's increasing. And conversely, if the difference is negative, the sequence is decreasing, because we always have to subtract a number from the previous term. And if the ratio is less than 1, that means each term will be smaller than the previous term, so that the sequence will be decreasing. So for this sequence, we're going to look at the difference between two consecutive terms. So we just take a of n plus 1. So we just replace the n's with an n plus 1 to get n plus 1 over n plus 2 minus a of n. And so if we subtract these fractions, it simplifies to this expression. And since n is always positive, this difference between these two consecutive terms is always positive as well. So this sequence is increasing. Now sometimes we'll have a sequence like this where the beginning is a little random, but after this point it is clearly an increasing sequence. So if we can ignore some terms from the beginning of a sequence, and that makes it the rest of it have a certain property, then the sequence has that property eventually. So if we ignore the 9 through 12, then the sequence becomes an increasing sequence. So this sequence as a whole eventually increases. And we test for eventually increasing or decreasing the same way that we test for regular monotone. So in this example, we want to prove that it's eventually decreasing. And to do that, we're going to look at the ratio between two consecutive terms instead of the difference like last time. So we take a of n plus 1 over a of n. And if we simplify this, 10 to the n plus 1 power is just 10 to the 1 times 10 to the n. And likewise, n plus 1 factorial is just n plus 1 times n factorial. So that allows us to cancel out some terms in this ratio, leaving 10 over n plus 1. And so we know that if the ratio between two consecutive terms is less than 1, the sequence is decreasing. So we see that from n equals 10 and beyond, the ratio is always less than 1. So after n equals 10, the sequence is decreasing. So this is eventually decreasing sequence. And if we have a monotone sequence, then only one of two things can happen. It either converges or diverges to positive or negative infinity, because a monotone sequence cannot oscillate. And so this is based on the existence or non-existence of a bound. So for an increasing sequence, if there is an upper bound such that the sequence never is always less than that upper bound, then that means the sequence must converge to a limit, and that limit is less than or equal to the upper bound, because it never passes that. And if there is no upper bound on an increasing sequence, then it must diverge to positive infinity. Likewise, for a decreasing sequence, if we have a lower bound, so some number that the sequence never goes below, then the sequence converges to some limit that's greater or equal to the lower bound. And if there's no lower bound on a decreasing sequence, it'll just keep decreasing all the way to negative infinity.